Okay, so as you know, with the ERIC flash floods, one of its inputs is the soil moisture that comes from list flood. So when we change the calibration of list flood, we then need to go back and change the climatological data for ERIC and also to reevaluate the thresholds that we use for the flash flood notifications. So I'll just talk you through what we did for the EFAS 4.0 release. So basically, once we had the list flood long-term run available, we recomputed the climatology for ERIC. So that means between 1991 to 2008, we use the Cosmolabs limited area model reforecast as the meteorological input with the soil moisture from the list flood long-term run. And we compute the annual maxima series for ERIC, and then we compute things like the mean annual maxima and the return period thresholds. And then the next step of that is we need to see if we need to change the notification criteria for the flash floods. So what we've done this time is we've tried to have a much longer evaluation periods. Before it's been about 3 months or so. This time we've run our evaluation for a year. So we chose the year of 2019 and we reran the ERIC forecast using these new inputs for the entirety of that year, making forecasts on each day at 0, 0 and 12. And we obviously make the forecasts at all the different lead times up to 5 days ahead. And then we're comparing these against observations, which we've sourced from a combination of sources such as FloodList, the European Severe Weather Database, as well as the Austrian EFAS partner. We also got observations from the UK Flood Forecast Centre, but at the moment they needed a bit more cleaning to kind of differentiate between flash floods and non-flash floods. So we ended up with a total of 2,655 observations, but these are at a point scale. So what we needed to do is aggregate them onto the administration regions layer that we use to issue the flash flood notifications. So that's what we've done, and after we do that, we end up with it's 545 sort of unique instances of flash flooding across the domain. So the figure on the right-hand side here shows which region, shows the total number of days that there was flash flooding in each of the regions where we had observations. So if a region isn't shown, say like most of France or in northern Germany, that's because we didn't have any data. You can see that in Austria we have a lot of observations, and that's because we were provided with a lot of observations. It's also worth pointing out that we had to apply some filtering to some of the European Severe Weather Database data, because it's things like it's very localized that we can't really expect our sort of rather coarse model to get. So we said there has to be a minimum of 5 data points from that data set in a given region for it to actually count as an event. So what we then do is with our ERIC forecast that we've made for 2019, we applied different exceedance probability thresholds to the 2, 5 and 20-year return periods to generate different warnings. These are then compared against the observations and we calculate the hits, misses, false alarms and the correct negatives. If we go to the next slide, please. So the results, so we computed the skill using this Hansen-Kuiper's skill metric, which shows how well you can separate between an event and a non-event, so a flash flood and a non-flash flood. And I mean, the best results came when we're using the 5-year return period as our sort of not baseline. But you can see at the graph on the right here, it shows different exceedance probability thresholds of the 5-year return period. So going from 0% to 100% exceedance probability, and the different lines show different lead times. So the dark line, the black line shows 1-day lead time, blue is 2-day, green is 3-day, and it shows that the sort of 10% exceedance probability threshold of the 5-year return period gives us kind of the best results up to around about 3 days lead time. So just breaking down that performance seasonally, and just trying to break it down as well into hits, misses and false alarms. If you look at the graph on the bottom left, so for this 10% exceedance probability of the 5-year return period, you can see that in winter we end up with like quite a lot of false alarms, in summer we end up with quite a lot of misses, and in autumn you kind of get a mixture of the two, but you get more hits. So in a way, autumn was the sort of the time where ERIC had the most skill in breaking it down spatially. That's sort of distributed along the eastern coast of Spain and southern France, whereas when you go into winter, we kind of got quite a few false alarms in Italy and the Balkans, whereas in the summer you get these kind of convective events which are really difficult to capture.